This meeting is being recorded.
This next example from chapter 14 is sample exercise 10, and we're given the information here for a first order reaction. We have H2O2, liquid, which it decomposes into liquid water and oxygen gas. So this actually happens to hydrogen peroxide. So this solution here begins at 0.6 molar, and it's found to be 0.075 after almost an hour. So 54 minutes have elapsed here. So we're asked to calculate our rate constant. So if you remember, the integrated rate law for a first order reaction takes this form here, where we have our concentration at time t will be equal to the negative rate constant k times that time that has passed plus the natural log of the initial concentration. So given these values, this is my a sub t, this over here is my initial concentration, and this is my value for t. I'm going to plug these in, and we would see that the natural log of 0.075 will equal negative k. Our time is 54 minutes. And then we're going to add to that the natural log of 0.6, our initial concentration. So let's write this line down below here. So take the natural log of 0.075, we get negative 2.590. And we can actually combine these here. So that would be negative 54k now. And then plus, we have a negative value that results. The natural log of 0.6 is negative 0.5108. So let's add this value to both sides to cancel out. So we have an additional 0.5108, and after combining like terms, now we have negative 2.079 over here, and that equals negative 54k. So we divide both sides by negative 54, and our k, our rate constant for this reaction, turns out to be 0.039 per minute, because our time t was measured in minutes. So we're asked in part B here to figure out what the half-life is for this reaction. So we know for a first order reaction that the equation t to the 1/2 will equal the natural log of 2 divided by the rate constant k. So if we're asked to solve for this here, all we have to do is calculate, plug in natural log of 2. That gives us 0.693. And then we divide by 0.039 per minute, rate constant k. And that gives us approximately 8 minutes for our half-life. Now, this was another example of a first order kinetics reaction, but we see the next thing mentioned on our worksheet here is for a second order process. So we can derive the half-life equation for a second order process as well, and it would turn out to be this here. So you should note that half-life depends on the initial concentration of the reactant when we have a second order reaction. And then we saw that when we have a first order reaction, it does not depend on the initial concentration. So this table here has a summary of the different orders of reaction that we have seen, 0th, first, and second, the corresponding rate laws. That would be examples of each. The integrated rate law that we use to solve for either time that has elapsed, a rate constant, or how much concentration remains after a certain time. We even have what would create a straight line plot. So, for example, a zero order reaction, our y value being concentration versus t, this would give us that straight line plot. And then the last column here summarizes all three half-life equations.